Hello everyone, this is Dr. Abdul Pasha. Power system operation and control. So here now I am going to give presentation on optimum load dispatch including transmission losses. So earlier class we have seen that optimum load dispatch including, that is excluding transmission loss coefficient, utilizing a simple flow chart. So here also the same procedure will be implemented, but here we are supposed to be including the transmission loss coefficient. There we excluded the transmission loss coefficient. Coming to this, consider whatever the image here shown. With this, we are supposed to be shown with two presentations of the generators 1 and 2. So with that, two identical generators, incremental production cost will be represented. So if the generator 2 has a local load, according to equal incremental production criterion, the total load must be shared equally. So this will be done by both the generators. That is, each generator should supply half of the total load. So the common sense tells us that it is more economical let the generator 2 supply most of the local load, because generator 1 has to supply in addition to the load case. So the transmission loss is also supposed to be considered here. So therefore, criteria of sharing the load by equal incremental production cost may be varies that does not hold well under such situation, and a strategy must be evolved which takes in account of the transmission losses also. So here are our two generators, that is generator 1 connected here, and this is our generator 2 connected here. So this is connected by a common load, that is this one. So this is represented with one of the complex parameter R plus Jx. So the optimal load dispatch problem including transmission losses are defined as minimal cost, that is f suffix t is equals to summation n equals to 1 to n small n fn. So which will be subjected to Pd plus PL minus summation n equals to 1 to n Pn equals to 0. So here PL is the total system loss of the entire power system network. So which is assumed to be a function of generator, and the other term have their usual significances. So making use of the Lagrangian multiplier, that is lambda, the auxiliary function can be represented by f. So that is f equals to ft plus lambda of Pd plus PL minus summation PL. So the partial differentiations of these expressions when they equated to 0 gives the condition for optimal load dispatch. Now the condition for optimal load dispatch is dou f by dou Pn, which is equals to dou ft by dou Pn plus lambda of dou PL by dou Pn minus 1, which is equals to 0. So if you equate to this dfn by dpn plus lambda dou PL by dou Pn, which is equals to Lagrangian's coefficient. So this is represented by equation 1. Here the term, this is known as the incremental transmission loss at a plant n, and lambda is the one of the Lagrangian's coefficient, as the incremental cost of the received power is in megawatt hours. So the above equation is a set of n equations with n plus 1 unknowns. So here n generators are unknown and lambda is also to be unknown. These equations are known as coordination equations. So because they coordinate the incremental transmission losses with the incremental cost of the production. So to solve such type of conditions or equations, the loss formula equation is supposed to be expressed in terms of its generator, and it's approximately represented as PL equals to summation M summation N PM BMN PN, which is about equation 2. So where PM and PN are the source loadings. That means BMN is the coefficient of the transmission loss, and the formula is derived under the following considerations. The considerations here: the equivalent load current at any bus remains a constant complex fraction of the total equivalent load current. So the generator bus voltage magnitudes and angles are must be constant. That will be considered as one of the assumption in this system. So the power factor of each source is considered as constant here. So solution of that coordination equation requires the calculation of dou PL by dou PM. So which is obtained from equation 2 as dou PL by dou PN equals to 2 summation MBMN PM. So dFN by dPN equals to FNN PN plus small fn. So the coordination equations can be rewritten as FNN PN plus Fn plus lambda summation 2 BMN PM is equals to lambda. So collecting all the coefficients of PN, we get Pn of Fnn plus 2 lambda Bnn is equals to minus lambda summation m naught equals to n 2 Bmn Pm minus Fn plus lambda. So solving for Pn, here we get Pn equals to 1 minus Fn by lambda, which is about summation m naught equals to n 2 Bmn PM. So this is the condition we will obtain with the denominator case of Fnn by lambda plus 2 Bnn case. So this is equal to Pn consideration. So to arrive at an optimal load dispatching solution, the simultaneous solution of the coordination equations along with the equality constraint should suit, and any standard matrix inversion subroutine could be used here. So here it is the case of flowchart representation. This is the consideration for transmission losses included. That means flowchart representation for economic scheduling when transmission losses are included. So what are the transmission losses we expected means the basic transmission losses here are because of due to distance, which will be larger, and another case is presence of reactance, and another case is due to transformer losses, and one more thing is that this is because of resistance, and also due to the presence of corona. So all these considerations make the happening of these transmission losses. Now we will start with the flowchart case. So this is the starting point. Here we will read FNN, FN, PD, PN min and PN max. So these are the variables we should define first. After that, assume a suitable values of lambda and delta lambda. Now determine Pn corresponding to incremental cost of production. So here first set k value to 0 and set n equals to 1. Now solve for Pn, then it becomes 1 minus Fn by lambda minus 2 summation m naught equals to n Bmn Pm, which will be divided by Fnn by lambda plus 2 Bn. If Pn greater than Pn max, if it is this condition is possible, that means Pn equals to Pn max. So if Pn less than Pn minimum, when this condition is satisfied, then Pn equals to Pn minimum. So like that, the total consideration will be about when it is not executed, n equals to n plus 1 will be taken place. So if it is not possible, check if all the buses have been accounted, then it should not be possible means then we have to go for again solving of Pn. So if it is possible, checking if all the buses have been accounted, then we should say that Pik minus Pik minus 1 less than E. So that means if this condition also not satisfied, then K equals to K plus 1. Then if it is satisfied, calculate PL. So here summation n, summation m, Pn, Bm, and Pm, where delta P is summation Pg minus PL minus Pm. So if P delta P less than or equals to E, that means this is accepting means print the generation and calculate cost of generation. So by this it means if it is not possible, then we have to go for delta PP calculation. So here summation Pg minus PL minus PD will be taken place. So if not, it is delta PP greater than 0. So that may equate, then lambda is lambda minus delta lambda. If it is not possible, then lambda equals to lambda plus delta lambda. So after this, if this condition is not accepting, then we have to go for here and setting the k value equals to 0 again, and again repeat the process from starting onwards. So likewise the process will be repeats number of times. General transmission line loss formula. So an exact formula for calculating the transmission losses are derived by making use of the bus powers. That means it also considers the system parameters. So let S into I be the total injected bus power at bus I, and it is equal to the generated power minus load at bus I. So this is indicating S suffix I. So this is equal to the generated power Pg minus load at bus I. Load at bus I. So this consideration must be taken. So the summation of all such powers over all the buses gives the total losses of the system. That is PL plus JQL is equals to summation I equals to 1 to n Si, where S suffix I is the power that should be treated here. Total injected bus power as an excitation. So this complex power can be splitted as VI conjugate. We already know this condition. So S equals to VI conjugate. So this is happened at respective buses, V bus, I bus. So conjugate term is considered. So here PL and QL are the real and reactive power loss of the systems. V bus and I bus are the column vectors of the voltages and currents for all the respective buses. So V bus equals to Z bus into I bus, where Z bus is the bus impedance matrix of the transmission network, and it is usually given by Z bus equals to R plus JX, which can be written as R11, R12 up to so on R1n. Similarly, R21, R22 up to so on R2. This will be continued till Rn1, and this will be continued till Rn2, and this will be continued till Rn. Like this equation will be follows, and this resistance parameter R will be added to the reactance parameter X, that is X11, X12, so on up to X19. Similarly, X21, X22 up to so on X2n, it will be taken place. And this may ends up to Xn1, Xn2 up to so on Xn. So likewise, the matrix will be followed as Z bus, and which is the combination of R plus Jx. So this is in complex nature. So from the above equations, we may suppose it to be right PL plus JQL equals to I bus transpose Z bus transpose to I bus complex case. So when you simplify this I bus transpose Z bus into I bus, you may obtain finally for PL plus JQL case. Here where real and reactive terms are considered as a complex in nature. So the last step can be written because Z bus is a symmetric matrix. Remember that here Z bus is a symmetric matrix, that is impedance bus, and therefore that symmetry can be represented in terms of its transpose case. That is Z bus transpose equals to Z bus star. So the bus current vector I bus can also be written as the sum of a real and reactive component of the all the vector positions. We need to remember this. Bus current vector, that is I bus, can also be written as sum of the real and reactive portion. That means P plus JQ combination. This is called real and reactive powers summation combination. And after this, we need to extend the analysis with the current bus, that is I bus IP plus JIQ. So what it enables us that IP1, IP2 up to so on IPN are considered. So this will be the real term coefficient P in terms of the current, and the reactive power coefficient is Q, that is IQ1, IQ2 up to so on IQN is considered. So the equation for the loss can be written as PL plus JQ, which is IP plus JIQ whole transpose into R plus JX into IP minus JIQ. So this is the combination we will consider. So separating out the real part PL from the above matrix product, we will get PL equals to IP transpose RIP plus IP transpose XIQ plus IQ transpose RIQ minus IQ transpose XIP. So since X is a symmetric matrix, so IP transpose XIQ equals to IQ transpose XI. So PL equals to IP transpose RIP plus IQ transpose RIQ. So the above expression what we written here can be rewritten by using index notation. So what it represents, index notation means PL equals to summation N I equals to 1 to K, that is K equals to 1 RJK IPJ plus IPK plus IQJ IQK. So like that we will represent this combination as PL. So after this consideration, the transmission loss has been expressed in terms of its bus currents. The transmission loss has been expressed in terms of its bus currents, that is in an actual power plant. The system operators usually knows the bus powers and the nodal voltages. So it is therefore more practical to express this PL coefficient in terms of these quantities. So because of this, for the n number of buses, for bus powers, at bus I we have the coefficient Pi plus JQi equals to Vi conjugate in terms of ith columns. So this may be the product of Vi of IPi minus JIQ, which is equals to magnitude of Vi of cos delta I plus J sin delta I into IPi minus JIQ. So where delta I is the phase angle of the voltage Vi with respect to the reference voltage, that is slack bus voltage. So here slack bus voltage is taken as reference voltage. Now separating the real and imaginary components or parts, then we have real part is Pi, reactive term is Q, that is imaginary term. So real term is with ith element, modulus of Vi cos delta I IPi plus Vi IQi sin delta. Similarly, Qi equals to Vi IPi sin delta I minus Vi IQi cos delta. So solving for these conditions about for IPi and IQi, we will get IPi and IQi conditions. So all these two currents may taken place at ith element. So 1 by modulus of Vi Pi cos delta I plus Qi sin delta. So IQi can be represented as 1 by Vi Pi sin delta I minus Qi sin delta I. So these are the two currents we will obtain solving for these expressions. After this, we have to express the real and imaginary components of the bus currents in terms of its bus powers and also in terms of its bus voltages. Now substituting these values in the expression of power loss coefficient, we will get after some algebraic manipulations. So what are the algebraic manipulations we done means we will get a PL that is j equals to 1, k equals to 1 to n small n alpha jk of pj pk plus qj qk plus beta jk qj pk minus pj. So alpha jk is equals to rjk by vj vk cos delta j minus delta k. Similarly, beta jk as rjk by vj vk sin delta j minus delta k. So by making use of these expressions with these alpha and beta, we may say that transmission losses along with the coordination equations, the problem of optimal load dispatch can be solved. So we should utilize these conditions in terms of alpha and beta, and we are making the coordination equations, then the problem of optimal load dispatch can be easily be solved. So another factor in optimal load dispatch including transmission losses are denoted with the penalty factor. So from the coordination equation, what is the coordination equation we derived? df1 by dpn plus lambda dou pl by dou pn equals to lambda. So this dfn by dpn equals to lambda of 1 minus dou pl by dou pn. Simply we are taking the common here on either sides and writing like this. So dfn by dpn into 1 by 1 minus dou pl by dou pn equals to lambda. So this dpn by dpn into ln gives one of the Lagrange's coefficient lambda. So where ln is the penalty factor of a plant n, for a given plant n, the penalty factor is represented with ln, L suffix. So, and it is given by the condition ln equals to 1 by 1 minus dou pl by dou pn, which is equals to 1 plus dou pl by dou pn, that is approximate penalty factor. This is the condition for approximate penalty factor. So this approximation can be derived with one of the loss coefficients, and it will be applicable for suitable power plant case. So here the control over towards this penalty factor can be derived easily with the considerations of components in equality constraints. So these constraints makes the penalty factor to be simple while deriving the expressions in such a manner. So here the coefficient with ln as dou pl will represent the change in load case and dou pn will represent the change in plant factor. This change will represent 1 minus the total ratio. And if you make this condition by removing numerator term, then it will be added to 1 plus dou pl by dou pn case. So here this will be one of the approximation of penalty factor. So what happens with this approximation of penalty factor means we can substitute the corresponding PL and PN values, then approximation is done means the amount of power that should be transmitted over the transmission network, they should suppose to meet the load requirement or not. That can be we decided with the penalty factor consideration. So this will better defines about the response generated from the generator case should meet the load requirements or not, or some other loads has to feed to the load. So with the help of these conclusions, we can suppose to release the amount of power to the respective load conditions. So these generators are ready to feed the power wherever the lagging mismatches to the system. So this mismatch can be neutralized by filling its gaps with the number of units or number of generators connected in the line. So due to which the penalty factor coordination may also considered with alpha and beta coefficients also. So due to which what happens means whatever the problem that we are facing in optimal load dispatch, that can be solved easily. So this procedure will help in determining the best optimal load dispatch including the transmission losses. So when transmission losses are more, then penalty factor also increases. So we have to cross check that based on the transmission loss coefficient, how penalty factor is going to be varies. So these are the considerations we must assume. According to that, we should plan for the minimization of this transmission loss coefficient by avoiding this distance parameter and one of the reactance parameter and transformer loss coefficients and one of the corona discharge conditions. So by minimal case of whatever the parameters which are making the loss coefficients to be more, that should be minimized, means we can improve the efficiency of the system, generator efficiency of the system, and by that the transmission network can also be smoothly transmit the power over long distances. So this is to the limited extent, means the transmission line can only ready to transmit the power only suitable distant levels. So if you are expecting more power transmission from one end to another end, means you are going to expect heat loss more. So these are the considerations we need to taken into the account, and based on that, the optimal load dispatch scheduling can be takes place, even though the transmission losses are included. So if it is the case of excluding the transmission losses, we cannot suppose to define the suitable condition of the load requirement for n number of generators or n number of units. So this is the reason we should go with the optimal load dispatch with the consideration of transmission loss coefficient. So these are suitably fulfilled by one of the B coefficients. We already derived in terms of B112, B33 in a matrix formation. So these will resultantly coincides with the Lagrange's coefficient, and they give the better results in defining the one of the cases. And coming to the references, so these are the references I opted for getting the better results in explaining the transmission loss coefficients and also the flow chart considerations. So, and some of the video lectures helpful to define one of the parameters associated with flow chart considerations and website resources and textbook PDF considerations. So for economic dispatch including transmission losses, then these are the two conditions will better suitable for optimal scheduling of the generators. So thank you for listening.
Like, share and subscribe. Hit the bell icon for more updates.